Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll begin a new unit of probability and we'll start with the topic of conditional probability. So let's start with a brief recap of what probability is in general. We look at the total number of events that are possible and we look at the number of desirable events for the probability. So let's take a simple example. Let's say we flip a coin 3 times in a row. So there could be a total of 8 combinations. Heads, heads, heads. You could have 1 tails, which could be in 3 different positions. You could have 2 tails. And you could have 3 tails. So if you flip a coin 3 times in a row, this is the total set S of all the events that can happen. Right? There are a total number of 8 events that could happen. Either you could have 3 heads or 3 tails, or 2 heads and a tail, or 2 tails and a head. Each and one of the last 2 could happen 3 different ways. Let's say you have another set of events, E, which is that we have at least 2 heads. So out of the 3, we have at least 2 heads. So we could have 3 heads, or we could have 2 heads, which would be H, H, T, H, T, H, T, H, H. These are the total. These have at least 2 heads. The total number of events is 4. Let's look at another set F, which is the set of events such that the first toss gives a tail. So here the first one is heads, here the first one is tail. We want the first one to be tail. So you can see it's the lower 4, not the upper 4. So it'll actually be, sorry, it's not this one, not HTT. So it's THH, TTH, THT, and TTT. So once again you have 4 possible samples. So these are basically sets. We've already seen sets and relations before. Now we start looking at probabilities. What is the probability that event E can occur? Right. So what the total number of things that can happen is 8. You could have HHH, HHT, HTH, THH, TTH, THT, HTT, and TTT. So you could have 8 total possibilities. Out of them, 4 include the condition E. E was the set of all events where you have at least 2 heads. So out of those 8 possibilities, you have 4 possibilities where you have at least 2 heads, and those 4 possibilities are given in E. So the probability that E can happen will be the number of possible ways E can occur by the total number of ways, which in this case would be S. So this is the number of ways E can occur. E is a set of events. Every event occurs. By S. S is the general set which we'll denote to denote the total set. So we would write this as total number of events. In this case, we would have the number of ways E can occur would be 4. And the total number of events is 8, which comes out to be 1 by 2. Right. Also, similarly, we could look at the probability that event F occurs, which means that the probability that the first toss gives me tails. Now, there are actually 2 ways to look at it. One is you just look at the number of ways F can occur, 4 divided by total number 8, which gives me half. But if you think about it a little bit, F is a set of events where the first toss gives me a tails. No matter what happens in the second and third toss, the first toss has a 1 by 2 probability of giving you heads and 1 by 2 probability of giving you tails. For F, you can directly see that the probability should be 1 by 2. Now let's go a little bit further. I'll just rub the unnecessary part. So now there are two other things which we can look at. One which will not be useful in this example is E union F. We know what that is. That will be the set involving all the elements of these two sets. So if you look at it closely, there is one element which is common, THH. So we don't need to repeat that. So it will be HHH, HHT, HTH, THH, TTH, THT, and TTT. Right, and union basically is sort of like the OR. This is the probability, sorry, this is the set of events in which either A is true or B is true. Right, in this case either E is true or F is true. Right, so if E is true, it belongs to E union F. If F is true, it also belongs to E union F. Then you have what is called E intersection F, which would be the set which has elements which belong to both E and F. There is only one element, THH, which belongs to both E and F. So E union F will simply be THH. This has a total of 7 elements, 1, 2, 3, 4, 5, 6, 7. This has only one element in it. And this is the probability that both E and F occur. That means you have two, this is THH. Yeah, you have two heads, but you also begin with the tails. So there is only one. Now you can have other probabilities as well. By the general definition, probability that E union F will simply be number of events in E union F by the total number of events, which will be 7 by 8. 8 is the total number of events. Only case in which that is not occurring is HTT. And if you want P of E intersection F, which means both E and F are true, that is number of E intersection F by number of S, which is 1 by 8. Right. Now we can look at something which is called the conditional probability. And the conditional probability, in this case the condition would be F. We can choose either one of them. So it would be written as E, and then you have a bar and then F. So this is a new thing. It's not a union, it's not an intersection, it's something new. P E bar F. The definition of this is the probability that E occurs given that F occurs. So it's a conditional probability. F has to be true. Right, the probability that E occurs given that F occurs. So obviously we don't need to take HHH because F does not occur in HHH. Right, we need it to start with the tails. So the probability that E occurs given that F occurs. So before using the actual formula, let's just try to calculate its value. If F is occurring, that means one of these 4 events has to be occurring. So now what happens is, earlier our total sample size was this, which had 8 elements, but we are already told that F happens, F occurs. In that case, the sample size reduces from these 8 events to these 4 events. So now the denominator N of S, the total number of events, will actually be 4. And out of all those 4 events where we know that F occurs, how many of those events are such that E occurs in it as well? So THH, we know that E occurs here, but the other 3 are not elements of E. So only THH will be the case where E occurs given that F occurs. When you have HHH, E does happen, but F is not happening. Similarly for HHT and for HTH. So you can directly see the probability is 1 by 4. This can be written in the more general form as number of cases of E union F. So this thing, basically E and F both have to happen, but the denominator is different. Now the total sample size is not S, because we already know that F is happening. That means all 8 of these are not a possibility, only 4 are possible. So only 4 of these are a possibility. So n of f, which n of E union f we know is 1 and n of f we know is 4. Right, and what we can also do this is we can divide both the numerator and denominator by n of s. So n of E intersection f by n of s by n of f by n of s, and what this comes out to be is, look at this box above, p of E intersection f by p of f. Right, I'll just write it here, p of E intersection f by p of f. So this is basically the definition of conditional probability. Now we'll forget the heads and tails and I'll just explain a little bit more once more. P of E bar f means the probability that, now the correct language is not really the event E, the correct language is an event in the set E. Given that conditional probability, an event in the set F occurs and it is equal to the number of ways both E and F can happen divided by the total number of ways F can happen, which is also equal to the probability of both E and F happening by the probability of F happening. Remember, F is not generally certain, right? When we were tossing 3 coins in the air, the first one does not need to be heads, but then we were given that the first one is heads. Sorry, F was tails. So once we were given the first one is tails, the equation completely changes because we have to forget every case in which the first one is not tails. So P of F is the probability that F happens. P of E union F, intersection F, is the probability that they both happen, and this is out of a total set of S. Right, and here number in F would be 4 and number of E intersection F would be 1. Now there are a few properties of conditional probability which we learn because we'll be using some proper equations in terms of conditional probability. So the probability of S given that F happens, this is the first property, we'll do 3 properties, is equal to the probability F conditional F is equal to 1. So what does this mean? The second one is quite simple. Given that F happens, what is the probability that F happens? Well, so this is sort of redundant. It comes out to be 4 by 4, which is 1. However, PS of F is, given that an event in the set F occurs, what is the probability that an event in the set S occurs? Well, S is the total set. No matter what happens, the event will be a part of the subset S. So we'll just try to write these properly. This first one can be written as P of S intersection F by P of F, right? And this one can be written as P of F intersection F by P of F. Now we already know F intersection F is basically F, so this is 1. And since S is a superset of F, S intersection F is P of F. Right, this is a property of sets we've seen in class 11th. P of S intersection F, where F is a subset of S, will be P of F by P of F, which is once again 1. So this is the first property. Let's look at the second property. Along with S and F, let's say you have 2 other events. They don't necessarily belong to the set F. They are events A and B, and they belong to the set S. So there are 2 random events in the sample space S. Then we have the equation probability of A union B as long as F happens. Basically saying that we know that F happens, what is the probability that either A or B happens? This is equal to P A conditional F plus P B conditional F minus P A intersection B conditional F. So the structure is quite similar to an equation you already know of the union, so we can just write this in the proper form. We know that the LHS will be P of A union B intersection with F. Yeah, because P of A union B given F happens is we'll take the intersection divided by P of F. Right, now we can use the distributive law. We know the distributive law when we have a union and an intersection with the bracket in between. So this will be equal to P of A intersection F union B intersection F. Right, so we just took A intersection F and then B intersection F, basically like opening the bracket. This is a property you already know. And then we have divided by P of F. And that can be written as, once again we'll use the distributive property, P of A intersection F plus P of B intersection F minus P of A intersection B intersection F. Right, this is a general property we know for union. A union B is equal to A plus B minus A intersection B. Right, and obviously you have divided by P of F everywhere. And this, you can easily see what this is. The first term is P of A conditional F. The second term is P of B conditional F. And the third term is minus P of A intersection B conditional F. So this is basically the standard distributive equation, and we have P of F in the denominator everywhere. And this equation, this is not generally very useful, you don't need to use it a lot, but this has a special case if A intersection B is the null set. That means A and B have no common events, right? The word for that to use is A and B are disjoint events. So for example, A could be that the first one is heads and B could be that the first one is tails. They can never be true together, so they are disjoint events such that A intersection B is the null set. In that case, this third term will be 0 and we will simply have the simple result which you will use quite often. The probability that A or B happens given that F happens is equal to the probability of A conditional F plus the probability of B conditional F, but this is only true if A and B are disjoint events. And let's finally look at one last property. This is for the complement. The probability that the complement of E happens given that F happens is equal to 1 minus probability of E conditional F. Right. So from a previous property we already know that P of S conditional F is equal to 1, and that we can write as P of E union E complement conditional F. Right, because S is the total set that will be equal to any set having a union with its complement. That is sort of the definition of a complement, right? And so that can be written as, because E and E complement are obviously disjoint sets, P of E given that F happens plus P E complement conditional F. From this equation, this is equal to 1. I obviously get the first equation, P of E conditional F is equal to P minus E given that F happens. Now let's look at one or two questions to give us a little bit of a feel of how to actually use these formulas. Okay, so it is given that there are 10 cards numbered 1 to 10 in a box. They are mixed up and one card is drawn randomly. So the total set of events would mean any one of the 10 cards could come up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total of 10 elements. The question is, it is known that the number drawn on the card is more than 3. So the number is greater than 3. What is the probability that it is even? So let's say the first condition E is that it is even. So for that we could have 2, 4, 6, 8 and 10. we would have a total of 5 elements. Let's say F is the set of events in which the number is greater than 3. So we would have 4, 5, 6, 7, 8, 9, 10. E intersection F would be the elements which belong in both of them. That would be 4, 6, 8 and 10. So this is a total of 1, 2, 3, 4, 5, 6, 7 elements. This is a total of 4 elements. We need to find PE conditional F, because what we need is the probability that the number is even, E, given that the number is greater than 3, given that F has already occurred. So this will be equal to probability of E conditional F by probability F, which is basically probability E conditional F will be 4 by 10 by probability of F will be 7 by 10. So this comes out to be 4 by 7. So otherwise the answer would be 1 by 2, 5 by 10. But if we know the number pulled is greater than 3, then there is a 4 by 7 probability that the number will be even. Let's look at another case in which we throw a dice 3 times. So we throw a dice 3 times, each one of them the number will be 1 to 6. So the total S, I'll not write all of the cases, but it will be a total of 6 into 6 into 6, which is 216 elements, because the first one could be 1, 2, 3, 4, 5 or 6. The second one could have 6 elements, the third one could have 6 elements. So the total sample size would be 216 elements. 111, 112, 113, 114, 115, 116, 121 and so on. Then we are given that event A is that we get 4 on the third throw. So the first and the second throw could be anything, the third throw has to get a 4. And B is given to us to be the event that we get 6 on the first and 5 on the second throw. We need P of A conditional B, means we need the probability of A given that B has already happened. Well, what will this be? P of A intersection B divided by P of B. So let's look at what each of these are. What is P of B? B, the set will be the elements such that 6 is on the first and 5 is on the second throw. So the only indeterminate one is the third one, right? So we could have 6, 5, 1, 6, 5, 2 and so on till 6, 5, 6. So this has a total of 6 elements. Then A needs to have 4 on the third row. So A, the first one could be anything, the second one could be anything, the third one has to be 4. So it will have a total of 6 into 6 is equal to 36 elements. Just like we got it here, 216. What is A intersection B? A intersection B is that we get 6 on the first throw, 5 on the second throw and 4 on the third throw. So there is only one element, 6, 5, 4. One element. Now we need PA conditional B, that is PA intersection B divided by PB. That we can see is equal to 1 by 6. 1 divided by 6, or you could write it as 1 by 216 divided by 6 by 216, where we actually use the probability. Here we use the number of events. Let's look at one final question to get a little bit more practice. We are given that a die is thrown twice and the sum of the numbers is 6. So the sum is 6. What is the probability that the number 4 has appeared at least once? So let's take this to be the event F, where the sum is 6 when we throw a die twice. So we get a 1, 5, 2, 4, 3, 3, 4, 2 and 5, 1. 1, 2, 3, 4, 5. A total of 5 elements. What about E? E is given to us to be the event such that the number 4 occurs at least once. So let's say the first one had a number 4. So we would have 4 1, 4 2, 4 3, 4 4, 4 5, 4 6. Then the second one could be 4. 1 4, 2 4, 3 4. And now here's the key part, 5 4 and 6 4. We won't have another 4 4 because we've already included that here. So there are a total of 11 elements. Right. What is E intersection F? So we need to have at least one 4. So you have 2, 4 and you have 4, 2, which is 2 elements. So P of E conditional F will be P of E intersection F by P of F, which can also be written as the number of events in E intersection F by the number of events in F, which is equal to 2 by 5. In the next video, we'll discuss one more important concept based on probability, that is the concept of independent events. Thank you.